As Todd said, my name is Felipe Madsen. I work at the National Rare Astronomy Observatory as a software engineer, a PhD in astrophysics. And I'm going to talk about how we've been using multiple GPUs on path to make our images, basically from the VLA. This talk is all about making images with the VLA. This is my abstract just for completeness. I will not read it for you. It's on the website. And quickly, the outline of my talk. So I'll be talking about what's current, what's the future for interferometry, then explain very quickly how I make images, and more on that later. The development of our process for compatible with HD Condor and high throughput computing, and then get into testing on path with multiple GPUs and talk show some measurements, a tool that we developed to see how well our runs are going on time, and talk about our challenges and what we have for the future. So this is what we currently operate. So the very large array that you just saw a picture of, and there's another one. So the very large arrays here. Then ALMA is, we operate along with international partners, and very long baseline arrays, 10 antennas distributed over the country, including Hawaii and Caribbean, to have very, very high resolution. And for the future, we are planning to combine all this in one kind of a combination of all this in what we call the NG-VLA. For a comparison, the VLA is 30 antennas, the 27 antennas, sorry. The ALMA is 65 antennas, and the NG-VLA is going to be 260 antennas, give or take. So it's larger than the VLA, than ALMA by orders of magnitude in different aspects, not only number of antennas. And we're expecting to have really much better images out of this. Well, Greg's talk was all Condor commands in 30 minutes. This is, I'll try to explain interferometric imaging in 30 seconds. And I have no hope of being able to do it. I love to talk about it. So if you want to talk about it, find me on the break. And if you're curious, I can explain this a lot more. In fact, I was talking to my colleagues yesterday for like 2 hours about this. So, okay. But basically, take the example of the VLA. This is the antenna positions of the VLA. This is the north arm, west, and east arm. From the antenna positions, we derive a sampling function by computing the distance between every two antennas and the orientation of that pair of antennas. So the northwest orientation and the distance. This will be, for each pair of antennas, there is a point in this plot here. So each pair of antennas, a point here, and we have this sampling function. Well, this is irregular and incomplete, not as incomplete as, for example, we saw a similar plot to this, the UV coverage of the Event Horizon Telescope earlier in the week. Well, their coverage is a lot more incomplete, but it's still incomplete and irregular. And we have to regularize this by resampling the data that we measure through this sampling function in a process we call gridding. And then we take the FFT, the inverse FFT of our measurements, and we end up with something like this. That is the dirty image. We call it the dirty image. And it's whatever is in the sky convolved with our sampling function. And we need to get rid of this sampling function and to end up with an image. And that's a lot of post-processing. And that process, that's called gridding. This is an iterative process where we revisit the gridding in every iteration, and this is very important for what I'll talk now, because what is the size of this computing? So when I started back in 2003 to make images with interferometers, I could process all my solar data from GMRT telescope in India that's very similar to the VLA. So I have 2 days of solar data at high resolution, and I could process all my solar data in 1 day on my Pentium 4 laptop. Well, those were good times because, well, first thing, the gridding that I meant. Oh, sorry. What happened? Oh. So first thing, the gridding that I mentioned is like 90% of our computing costs, approximately. And our data rate with the VLA is 25 megabytes per second, and for NGVLA, we're estimating it something like 8 gigabytes per second. Well, we already face challenges at this data rate. So we have 2 examples here that I'm using in my tests on PATH. So we have deep field observations with 9 terabytes of input data on 102 files. And we don't usually talk about our images in terms of megapixels, but this is something that everyone is used to now. So I calculated how big are our images in megapixels. And for this particular observations, they are 84 megapixels. And for our sky survey, that's a project to image the entire the visible sky to the VLA. It's over 30,000 square degree images, and each image is 268 megapixels. And so for the NGVLA, things get a lot bigger. The estimated size of computing is like 50 petaflops per second, which would result in a million wave parallelization with CPU cores running 24/7. And we estimate that with GPUs, we can reduce that to 1,000 wave parallelization. And that's to make one image. Okay. So we needed a high throughput, a model compatible with HT Condor high throughput computing to be able to go and, get whatever cycles we can from anyone who has cycles to give us to be able to process this. And what we do, so we developed this model for distributing our data processing, our imaging process, where we partition the data first. This is derived from our parallel implementation of TClean. That TClean is the task in our software Casa that makes images, the main task that makes images. And this is derived from this parallel implementation that currently runs on OpenMP, MPI, on a connected cluster. So here I make partitions of the data first and distribute the data to as many processes as I can. And so this light red, pink blocks here, modules here, are where I distribute data. So these are where I'm taking advantage of an HTC model. And these are the graders that are those hungry beasts for processing. And then I have to put everything back together in a serial step, which is part of our imaging cycle, and then scatter again to keep going with the process. So, well, because I'm very good at naming, just like, Greg used to talk about, Condor, I named it HT Clean, which I think it's self-explanatory. It breaks down this image processing in the process of breaking it down. It also addresses an asymmetry here, because when we parallelize this, we use a lot of uses a lot of flops and has a large memory footprint. And this doesn't use so much flops and has a much smaller memory footprint. And so this needs a much smaller computer. This is addressed when we break this into modules. I implement the iteration here using retry and PostScript. This is a subdag. This is another subdag. And we can partition the input data along various axes. We're currently doing time and frequency. We plan to do more, and I'll talk a little bit more about this in my next slide. Okay, so what did we need in order to be able to test on path? We needed a fully relocatable GPU grider. We needed to make tarballs of image products because our images are directories. We needed to improve the mapping of intermediate products, and we also needed unique names, which is related to the mapping, because using stash and caches, we cannot reuse names as we do in our process that takes advantage of shared storage. So our goals on this project is to measure the runtime scaling of our GPU grider that I'll show in a bit, to measure the runtime scaling of our distributed processing, and to prototype NGVLA scale data processing. Well, so this shows how a grider scales as a function of the number of the partitions of the input file. So I have two different input sizes here, 99 gigabytes and 198 gigabytes, and they correspond to these two parallel lines here. The solid lines are linear estimates, and the data is carried here. So they follow very well the linear calculations. To the side here is just as a function of partition size instead of number of partitions. So I combine all the data in just one plot. And even zooming in, we don't see a lot of deviation from a linear prediction. So they scale pretty linearly, pretty well, down from like 5 gigabytes to up to 200 gigabytes. That part is fine and shows that what we know that the grading is highly parallelizable. But we wanted to know how this was, how these processes were distributed in time, how concurrent we could run these processes, because remember, we also have a serial barrier. So we came up with the visualization that we call concurrency plot that will show how our processes are distributed in time. And well, this shows each process, how much processes are running concurrently, where are the serial processes, so where are the barriers, idle time, you know, and we have this is a view of an entire process. But we can also look into detail and, you know, see what is transfer time, what is job running but not our application running yet, how long our application is running. In the case of the grader processes, what is the grading time? You know, then again, how concurrent, how many machines, how many slots are running our jobs at the same time? And so we clearly see the serial barriers here, and I will talk a lot more about this in my next 5-ish minutes. So this is now, plotting the job wall time as a function of the number of partitions for the 198 gigabytes data set. Remember this, and then this is referring to that data set I spoke about in the beginning. That is, the images are 84 megapixels. So this is for our 198 input gigabyte input data, and this is comparing the time, the job wall time for the residual cycle, which is the grader process, basically, and our one of our serial barriers that's the gather. And so at 32 partitions, they take the same time. So I have a serial process, a serial barrier, and that this is not the entire barrier, this is just the first process in the serial part. This takes the same time as all the graders. Well, but this gets worse. Considering the same partition, so I took the same input data set, and I crafted a data set that was 99 gigabytes larger. So I kept the same partition size here and copied another 8 partitions and and ran with that. They are not expecting to have good images because I'm faking data, but just to keep this size of data partition and increase the number of partitions. And when I do that and then combine all the images, the gather time is here. So same job all time for residual cycle here, and the gather time is here. So this point is not here because I'm bad at because I have bad presentation skills. It's just because I wanted the plot, the point to be out of the plot because it's from a slightly different data set. So why does this happen? Because each partition will make a full size image. So this grows linearly with the number of data partitions. And now we have this, in this case, 32, then 48. And remember, we have to go to 1,000-way parallelization. So that will mean 1,000 partitions. And we are having problem at 48. This keeps growing. So 1,000 partitions, this will almost make our images impossible. And most of this job's wall time is transfer in and out and tar. Remember, our images are directories, and to transfer them, we need files. So for our sky survey, well, this is an example of imaging to convergence. So I ran many cycles here. So 4 imaging cycles here, that iterative process. And this is a well-behaved run. We didn't see much of idle time or anything. Thank you. And so this is just an example of how a well-behaved run would look like in the ideal world. But going back to that barrier, to that serial barrier, here is two different runs with our VLAS data from our sky survey that's showing the imaging cycle for 2 data partitions and 4 data partitions. These imaging cycles are comparable in duration. Here, the residual cycle took this much, and the gather, so 426, and the gather takes 188 seconds. Then for 4 partitions, 393, as expected, it decreases. But then the gather takes 238 seconds. So this is already showing that the same effect that I was. But this is at 4 data partitions, so a lot sooner. So what we have for the future? We want to improve the efficiency, the IO efficiency of our grading jobs. We want to get more job done with the same compute, with the same. So we want to further expand the data partitioning to other axes. So in my slide about that, I say what other axes we are interested in expanding the data partitioning to. Then we'll integrate a new model, new module to run the model cycle, but that's topic for another talk. And this gather barrier is right now is what we need to address in order to be able to scale up. So we'll optimize our deck design to minimize this barrier. We already have good ideas on how to do that, but we're also investigating scalable design solutions. So if any of you has a problem similar to this, please talk to me. And once we have all that, we'll scale up to our residual cycle partitioning to distribute by by at least 2 orders of magnitude, 1 to 2 orders of magnitude. And for that, we will need a larger number of available GPUs or a hybrid distribution model that does the grading on CPU and GPU. And that's all.